Let's do this problem from the lab assignment, section 4.7. A boat leaves a dock at 2 p.m. and travels due south at the speed of 20 kilometers per hour. And then we have another boat heading east, 15 kilometers per hour, and reaches the same dock at 3 p.m. So that's an hour. How many minutes after 2 were the two boats closest together? All right, so that's here's a picture of it. Our one boat is going south, and our second boat, well, it starts some time away from the dock, and this is supposed to reach the dock in 1 hour from 2 o'clock to 3 o'clock. So that means that that boat must have been 15 minutes or 15 kilometers away an hour ago, and then they would have moved toward the dock. Meanwhile, this other boat goes down. So I got a good graphic animation for this. We could take a look at it. Let me clear out a couple of things here. And let's start off with the two boats. So here's one boat going south, another boat going east. That's 15 miles or 15 kilometers away. And as they move, there's a distance between them. At some point in time, they're going to be closest to each other. And so we could take a look at this line as the distance between them. And so if we follow this line along, at some point that line is going to be the shortest distance somewhere, and then it gets long again. So it starts off 15 kilometers away, and then in the end it'll be 20 kilometers away. But at some points here in the middle, it's going to be shorter than 15 kilometers. And so that's what we want to find. All right, so that's our initial idea that we want. And so let's go back to our problem and see if we can fill in the blanks here. The southbound boat, corresponding when t is equal to 0, corresponds to the origin. Then the position of the boat heading south is the x-axis, or the x component, is always going to be at the origin, and then the y-axis is going to go down, so that goes down at a negative 20. So it's negative 20 times t, so 20 kilometers per hour times t, the number of hours. So we're looking at t as in hours here. Okay, so that's our first step. And then the position of the boat heading east. So this thing, again, it starts off 15 kilometers due east. So if we have this at the starting point, it's 15 kilometers east. So its actual position, if we have this on the x-axis like we do, its actual position is at negative 15, 0. And then it's going to move. As it moves, it's going to move towards the dock, towards the origin, assuming the dock is the origin, by 15 kilometers per t hours. So that's going to be your distance. So this starts off at negative 15, and then it doesn't go up or down the axis, it just remains on the x-axis. So that's going to have an x-coordinate, a position of 0. Alright, so now we have those pieces of information. The distance between the two boats is going to be given by this. So what we want to do is find the distance formula between these 2 points. So if we look at these 2 points, and this point, by the way, can actually be rewritten as negative 15. Negative is a positive, another 15. So let's put that 15 first. And then I think what they're interested in having us do is factor out of 15. So why don't we just factor it out here? So we factor out of 15, so we have a t minus 1. And now we're going to put that into here. So let's say this is my x x1 and y1. This is my x2 and y2. So my x1 is going to be 15 times t minus 1. So that's x1. And then your x2 is going to be the second point, the x value from the second point, which is 0. So your y1 is, in this case, going to be 0. And your y2 is going to be this value, which is negative 20. So negative negative is going to be a positive. And let's just knock out the 0 anyways. So if we knock out the zeros and look at these things as something squared, 15 squared, I believe that's 225. And then we have t minus 1 squared. And then here we have 20 squared, and I believe that's 400 times t squared. So that's going to be our distance formula. Okay, and like before, what we're going to do with our distance formula is we're going to square it, because the max and min for a square root of a function is the same as the max and min for the square of that square root. So it's going to be the square of the function, which is essentially taking out the square root. So again, this is 225, and this is t minus 1 squared, which, by the way, we can probably FOIL out. And this is going to be 400 t squared. And so this is what they have now, and then we're going to go ahead and FOIL this out so that we can have a nice function to work with. So f of t is going to equal to, this is 225, and in here is going to be t squared minus 2t plus 1. This is t minus 1 FOILed out, and then so we're going to distribute the 225 all throughout. So this is going to be 225 t squared, and then we have to double 225. That's 450. So minus 450 t, and then plus 225. This should be a plus. And now we can add the like terms. So this is going to be 625 t squared. So we have 625. There's an extra 5 there. So 625 t squared. And then 450. Oh, this is supposed to be a minus. 450. And a 225. Okay. So now we have a nicer polynomial to take the derivative of. We could take the derivative of this quite easily. We need to take the derivative of this. That would be 1250. That's 1250t and then 450. So let's put that in our notes over here. We have f prime of t is going to be 625 times 2 times t, and then minus 450. So now we're going to set that equal to 0. It's a nice linear term. So if this was set equal to 0, then we can just subtract both sides by 450, and then we'll divide by 1250. Okay, so that's going to be our our critical value. If we take the second derivative, we'll see that the second derivative will give us a positive value. The derivative of the first derivative is just going to be positive 1250, which is positive, which means it's concave up. And that means our critical value must be a minimum. And so we're going to have that. That's the local minimum that we want. So let's figure out what this is in our calculators. 450 divided by 1250 is 36.36. We want the minute, so this is 0.36 of an hour. So let's see, let's do approximately 0.36. Okay, so what we want to do is we want to translate this into time. So time is going to be this is 0.36 of an hour, and so we want to multiply this by minutes over hour. So 60 minutes over 1 hour. Let's put the labels here appropriately. 60 minutes over 1 hour. So the hours would cancel, and then I just multiply 0.36 times 60. Let's go ahead and do that. Times 60, and we got 21.6 to the nearest minute. 22. So 22 minutes. Okay, so that is in 22 minutes we have the boat that's going to be closest to each other. So I have this translated, my t parameter, into minutes already. So this is 0 minutes and this is 5 minutes. And if we look at 21, 22 right here, this looks like it's the shortest distance. And so what I did is I actually see if I graph the line and a point that tells you the distance. So if you look at the distance from the x-axis to this line, where that point is, that's going to be the distance. And so if you look at the distance going down, and it goes down at a minimum, and then it goes back up again. And then their distance gets to 20. So it starts off with a distance of 15 kilometers, and then it dips down. It goes down to about 12, and then it goes back up to 13, 14, 15, all the way up to 20. And if you look at the distance between the two boats, you can see that it does reach that minimum value somewhere over here when we have about 22 minutes. Okay. All right. So I hope that helps. I hope the visual helps, and more importantly, the calculations. Good luck.